Yes, ma'am.
Okay. So let's begin today's class. Any doubts or questions? I think some of you may have questions about the test that's coming up. Does anyone have any questions related to the test?
No, ma'am.
Okay. So I've shared the syllabus with you all. Please prepare accordingly. You don't have any R related questions for this test. Okay. So there's absolutely no practical work. It's simply theory based. Uh, so in the previous class, we were discussing co-integration. Okay. This is the class that I took. So any questions or doubts related to that? Okay. Nobody seems to have any doubts. So let's begin the class. Let me share my screen. Yeah. Okay, so for today's class, I had asked you all to just revise the portions related to rank of a matrix and characteristic roots. I hope you all have learned these things before. Have you all learned all this before?
Ma'am, rank we are partially
Okay.
aware of.
Okay. Characteristic roots, I think, are not familiar to you. Okay, so let's begin. I've tried to keep it as simple as possible, but we'll be using this in the next test for co-integration. That's why I need to cover some of the basics, all right, before I start discussing the test. So if you have a square matrix, okay, an n by n square matrix, which we are denoting by the term A, okay, and this matrix has these elements Aij. So each of the elements is denoted this way, Aij. I will refer to the row, J to the column. Okay. Now think that X is a vector, okay, which has n elements. Okay, so there are n rows in this vector. Now the scalar lambda is called a characteristic root of A. Okay, all of you are familiar with what is a scalar. Can anyone tell me what is a scalar? Anyone? Okay, even if you're guessing, you'll probably end up being right. You can see it in the equation here.
Ma'am, it's a multiplier. So basically, from a physics perspective, it's a quantity that has only magnitude, no direction,
Yeah. Okay.
or a single number rather than a
Yeah.
list.
Yes. Okay. So here you can just think of it as some kind of quantity or a number that you'll be multiplying. Okay. So this scalar lambda is called a characteristic root of this matrix A if this condition is satisfied. Okay. If you multiply the square matrix A with the vector, then you get the scalar multiplied with the vector again. Okay. So if this condition is satisfied, then lambda is called the characteristic root of A. Okay. Now we'll be using this lambda itself, these characteristic roots, again to find the co-integrating vector and so on. Okay, so that's why we are discussing this particular concept now. Now think of I. Okay, I usually denotes an identity matrix. This is also of dimension n by n. It's a square matrix. So you can rewrite this equation 13 this way. Okay. So here, uh, if you rewrite equation 13, okay, through some manipulation, you'll arrive at this equation here. Okay. So now, if you look at this particular equation, equation 14, okay, what we need is that the determinant of this matrix now, this will be another matrix, A minus lambda I, okay, will be another square matrix. So the determinant of this matrix has to be equal to 0. Okay. So as X is a vector which contains values not identically equal to 0. So there will be non-zero elements here. These will mostly be variables, but whenever you're using data and doing empirical work, of course, those variables will have some values. Okay, so that's why it's saying that these values will not be identically equal to 0. Okay, so that's why 14 requires that the rows of this matrix now, okay, A minus lambda I, should be linearly dependent. So if there's linear dependence in the rows of these matrix, of this particular matrix, only then the determinant will vanish. Okay, that is something you would have learned already when you were studying matrix algebra. So in other words, okay, 14 requires that the determinant of this matrix should be equal to 0. Okay? So can anyone tell me what does linear dependence mean when I'm saying the rows of A minus lambda should be linearly dependent? I'm just asking you so that others who may not remember, their memory will be refreshed.
The rows are not derived from each other.
The rows are not. Okay, yeah. Can you just express it in a slightly different way? You're correct.
Like first row is 2, 4, 6, and next is 4, 16, and 12. So basically that
Okay,
way
yeah.
dependence.
Okay, yeah. Okay, so there's no sort of linear relationship between the rows of the matrices. Okay, one row is not a multiple of another row or anything like that. Okay, so there's no linear dependence here. So, like you said, one row cannot be derived from the other row. Sorry about that.
That would be linear independence, right?
Yeah. So when you are able to derive one row from the other, yeah, then there is linear dependence. Sorry, I'm slightly distracted. Just a minute. Okay, so yeah, I was trying to talk about linear dependence, but I ended up talking about linear independence. Sorry. So that's
Yeah,
correct.
my apologies. I mentioned the opposite thing.
No, what you said was linear dependence itself. You said one row is a multiple of the other, right? That's what you were
Yeah,
saying.
but I thought that it should be independent. I misread this.
I think my question was dependent, so it's fine. Your answer was correct. I expressed it. I was talking about linear independence, I think. So here, 15. Okay, if you look at this equation now, equation 15 is called the characteristic equation of the square matrix A. Okay, so if you remember, even for difference equations, when we are finding the solution to a difference equation, there also we had a characteristic equation. Okay, so there also we were multiplying bn into a. Okay, something like that. We were deriving a whole equation and then finding out what are the characteristic roots of that particular equation. Okay, so similarly, even for a matrix, we are trying to do the same thing here. And equation 15 is called the characteristic equation of the square matrix A. Okay. Now, typically, the characteristic equation will be an nth order polynomial. Remember, your matrix A is an n by n square matrix. Okay. So, because of that, the characteristic equation will be an nth order polynomial which will have this form. Okay, so again, these are the characteristic roots. Okay, lambda raised to the power n. So you'll have in an since it's an nth order polynomial, and if you have a square matrix with the dimension n by n, okay, you'll have the same number of rows and columns in a square matrix. So here, for any square matrix, you'll have n characteristic roots for that particular matrix. Okay. So once you solve this characteristic equation, you'll be able to find the n characteristic roots for this square matrix A. Okay. There's a numerical example on the next page, so you all can try to solve that, so you might understand it a little better. Okay. So this will be an nth order polynomial, and once you solve it, you will be able to find the n characteristic roots of this particular matrix. Now, yeah, this is what I was talking about, that this matrix will have n characteristic roots. Okay. Now, the determinant of an n by n matrix is equal to the product of its characteristic roots. Okay, here this term has been cut out. Okay, this denotes the product of the characteristic roots. We are denoting the characteristic roots by lambda. Okay, so I will run from 1 to n. And for any square matrix, the determinant of an n by n matrix is always equal to the product of its characteristic roots. Okay, where lambda 1, lambda 2, lambda n are the n characteristic roots of this square matrix. If at any point you have a doubt, please stop and ask me questions. Okay. Now we come to the rank part of it, and we'll see how rank is related to the characteristic roots. Okay. So the rank of a square matrix is the number of linearly independent rows or columns in the matrix. Okay. So this is something you'll have learned before. One of you mentioned it earlier. Now we use this sort of a notation. Okay, rank of A. Since we are talking about the square matrix A, we'll continue to use that. So the notation rank of A is equal to R means the rank of A is equal to R here. Okay, so there are R linearly independent rows or columns in that particular matrix. So the matrix A is said to be of full rank if the rank of A is equal to n, which means there are n linearly independent rows and or columns of A. Okay, so whenever the rank of A is equal to n, it is said to be of full rank. Okay, which means all the rows and columns are basically linearly independent. Now the rank of A is equal to the number of its non-zero characteristic roots. Okay, so out of these n characteristic roots, how many of them do not have the value of 0? Okay, they are non-zero. That will give you the rank of the square matrix. Now, if all rows of A are linearly independent, the determinant of A is not equal to 0. Okay. Now, from 17, only if there is linear dependence, if all the rows are linearly dependent, then the determinant value will be equal to 0. Okay. Now, from 17, okay, what is equation 17 here? In this equation, that the determinant of a square matrix is equal to the product of its characteristic roots. From 17, it follows that none of the characteristic roots can equal 0 if the determinant of A is not equal to 0. So if you have a non-vanishing determinant, it means that none of the characteristic roots can be equal to 0. Okay, since the determinant of any square matrix is equal to the product of its characteristic roots. So even if 1 is 0, then the determinant is going to vanish. Okay. Now at the other extreme, if the rank of A is equal to 0, then each element of A must equal 0. Okay. These are certain laws, and you'll find that it is true. If you take numerical examples, then you'll find that this is true. So if the rank of A is 0, which means that all the rows are linearly dependent, rows or columns, then the characteristic equation will degenerate into this. Okay, so the polynomial will basically be equal to 0, and it will have solutions where all the characteristic roots are equal to 0. Okay, so that's why the rank of A will be equal to 0 again. Now for intermediate cases where the rank of A lies between 0 and n, okay, so some positive value, but it is less than n, it's not of full rank. In those cases, what we'll find is if you generally, if you interchange the rows or columns of a matrix, it does not change the value of the determinant. Okay, that's something you would have learned earlier also. So you can always rewrite this particular matrix A minus lambda I. This is the identity matrix equals 0. You can always rewrite this so that the first R rows, okay, will have the R linearly independent rows of A, and the remaining rows, your n minus R rows, there could be linear dependence in those rows. So you'll basically arrange the rows of your matrix in such a way that the first R rows, or the top portion of your matrix, basically has all the linearly independent rows. Okay? So the determinant of these first R rows will contain the R characteristic roots. Okay? The other n minus R roots will be zeros in that case. Okay? So generally, we usually deal, when we're talking about co-integration also, we generally deal with a situation where you'll find that the rank of the matrix is lying somewhere between 0 and n. Okay? It could be rank of the matrix equals 1. That's the most general case that we come across. Or it could be some positive value but less than n. Okay? So here there's a particular matrix which has been given. So I want you to try and find the characteristic equation and the characteristic roots for this. Okay, just try to spend a moment and do this for your own understanding. Okay, so you've been given a 3 by 3 square matrix A such that the rank of A is equal to 1. They've already told you that the rank of A is equal to 1. Okay, so just try and basically find the characteristic equation for this. Okay, and then solve to find the characteristic roots. I'll just give you a couple of minutes so that you can do this.
Ma'am, the determinant should equal to the rank, right?
Determinant should be equal to the rank. Why are you saying that?
Actually, I'm a little confused. How should we be going ahead with this, ma'am? Because I
Okay.
know.
Okay. I'll just tell you the first step.
Yes, ma'am.
So for the first step, just create this matrix now. Okay. You don't know what is lambda. Lambda is your unknown. So basically, create this matrix A minus lambda I. So you'll create an identity matrix which will have the same dimensions as A, obviously. Okay. So each element of this matrix, you'll be multiplying it by lambda. Okay, so I think you would have already understood what is your lambda I matrix.
Yes, ma'am. Understood
So
that.
yeah, so now create this matrix. Then after that, find the determinant of this particular matrix. Okay, and then solve for lambda. So when you try to find the determinant, the first thing that will happen is you will get the characteristic equation.
Yes,
After
ma'am.
that, when
Just
you
a
solve,
question.
yeah,
When we find the determinant, we have to equate it to something, right?
equals 0.
Equals 0. Okay.
Yeah, that's what you were asking me, is
Yes,
it?
ma'am. I was asking yeah.
Okay,
Should we equate it to 1 or should we equate it to 0?
0.
Thank you, ma'am.
Okay, once you finish, just let me know what your answer is. Determinant is equal to 0. Okay, then you have to find the characteristic equations and the characteristic roots. So you're basically trying to find out what is lambda. Okay, good. Next part. Keep solving and then
Ma'am,
yes.
so now in co-integration, instead of writing out for example, here the whole characteristic equation, we'll just use matrices and eigenvalue decomposition.
Yeah, you will be using the eigenvalues basically. So
Okay.
you won't be doing all this stuff actually when you're using the software. It does it for you. So this is just so
No,
you
ma'am, I
understand
meant
what it means.
mathematically.
Huh, yeah.
Okay.
Ma'am, is the value of lambda 0.8?
You will have how many values of lambda? See, it's a 3 by 3 matrix. So there will be how many characteristic roots? You'll have lambda 1, then you may be right. Okay. I'm just asking you a question. That's all.
We will get a cubic, so we will
Yeah.
at least have one solution.
Yes, ma'am.
Yes, that's correct. But how many characteristic roots are there for this equation? Since it's a 3 by 3 matrix, there will be
Three characteristic roots.
3 characteristic roots, correct. Okay, so you're saying at least one characteristic roots will have some positive value. That's what you're saying. Neil and
Yes, yes, sir.
the other person was Cherry, is it?
Yes, ma'am.
Ma'am, I'm getting 0 and minus 0.8.
Okay. Minus 0.8, is it?
Ma'am,
Yes,
I'm
ma'am.
getting positive 0.8.
Okay. Just check the person who got minus 0.8, just check maybe.
Okay, ma'am.
Okay, I'll just give you another minute. I think everyone should be able to finish by then.
I think the second answer might be right. With positive 0.8
Hmm.
and 0.
Okay. You should have 3, no?
Yeah, 0, 0,
Okay.
0, 0
Fine.
and 0.8.
Okay. Fine. Fine. So I hope, let's see. Yeah. This is the equation that you all got. Lambda cube minus 0.8 lambda square is equal
Yeah.
to 0. Yes.
Yes.
Determinant of A is equal to 0 and the characteristic equation is given by this. Okay. So the three characteristic roots are 0.8, 0 and 0. Okay. So why is the rank of A equal to 1? Can anyone tell me?
I think rank of the matrix is simply the sum across the diagonal, right?
Neil, you missed the first part of this class, is it?
Ma'am, R2 and R3 because of R2 and R3.
R2 and R3. Okay, the second and third row you're saying?
Yes, ma'am.
Okay. Can you say it in some other way, Rashi? You're correct, but I wanted
They're
to
a
state
ratio
it.
one another.
Okay.
All of the terms in row 2 and row 3,
Hmm.
if you divide them, you'll get the same ratio. Same.
Okay.
So basically,
Fine.
row 2 and row 3 will not give us any new information.
Okay. Fine. So basically,
Determinant, we can say that the uh, short least determinant is 1 by 1, non-zero.
okay. Okay, fine. I
That's
think
why the
And
rank is
similarly for R1 and R2 are like half. So that is
okay.
why
Yeah,
rank.
I get your point. So all of you are basically saying the same thing in different words, which is that there's only one linearly independent row here, okay, in this matrix A. So that's what I was looking for. All of you are right. Now, the other thing is, remember the rank of the matrix is equal to the number of non-zero characteristic roots. Okay, that's what we learned few minutes back. So again, you have only one non-zero characteristic root, which is lambda 1. Okay, so that's why the rank of A is 1 again. Okay? So I hope this point has been driven home now to all of you. So now we'll come to how are we applying this when we're studying co-integration. Okay? Any doubts or questions so far? Okay, I think we're good. Okay, so let's begin this part related to co-integration and the rank of any matrix. So this relationship is extremely important. The relationship between the rank of a matrix and its characteristic roots is very important in the Johansson procedure or the Johansson test for co-integration. Okay? So some of you have heard this name before. I think it was mentioned in the previous class. So to understand this test, the mechanics of this whole test, okay, we'll look at a simple var model and how we manipulate it and then put it in a form where we are able to conduct the Johansson test. Okay, so this is your typical form of the var model itself. Xt is equal to a1, xt minus 1 plus epsilon t. So this is a first order var model. We're taking a very simple var model to begin with. Okay. Now if you manipulate equation 18, subtract xt minus 1 from both sides. Okay. Then you'll get this equation here. Okay. So now in this equation, again, you can rewrite this, okay, so that you have xt minus 1 being common. So you create a new matrix A1 minus I, where I is an identity matrix, okay, with the same dimensions as A1. So you create this matrix and denote it by pi, okay, where pi is A1 minus I. So this is the form of our var model now. Okay. So what are xt and epsilon t here? Xt is your vector of all the variables that are there in your var model. Okay. So it's an n into 1 vector. There are n variables in your var model, so it's an n into 1 vector. Again, this is a vector of the error terms, white noise error terms. Now A1 is again a square matrix of dimension n by n, and it contains all the parameters in your var model. Okay. Then I is an n by n identity matrix. Now cointegration depends on the rank of the matrix pi. Okay. So what we try to do in the Johansson test is to find out what are the elements of this matrix pi, okay, so that we can find the cointegrating vector, and we also try to find basically the characteristic roots or the rank of the matrix, okay, pi again. So if R is equal to 0, okay, where again R denotes the rank of the matrix pi. Now cointegration depends on the rank of the matrix pi. If R is equal to 0, then it will mean that each element of pi must be 0. Okay, this is the same thing we were discussing earlier. So if all the elements of A are 0, then you'll find that the rank of the matrix A is 0. So similarly, if R or the rank of the matrix pi is equal to 0, it means that each element of pi must be 0. Only then that will happen. In that case, 19 will be equal to an n variable var in first differences. Since all the elements of pi are now equal to 0, this whole term will vanish and you'll be left with only delta xt is equal to epsilon t. So it will simply be equal to an n variable var in first differences. Okay? Or if I rewrite this equation, I'll be writing it as xt is equal to xt minus 1 plus epsilon t. Okay? Now since each xit is equal to this, okay, its lagged value plus the error term, all the xit sequences are unit root processes. Okay, remember that the coefficient attached to xit minus 1 is 1. Okay, no coefficient value is written, so you know that the coefficient is equal to 1. So all these n variables that are there in the vector xt are basically unit root processes or non-stationary variables. Okay, and there is no linear combination of these variables that will be stationary. Okay, remember that we need to find a linear combination of the variables which will be stationary. Only then the variables are said to be cointegrated. Okay, so that's why this statement is being made over here. Now at the other extreme, if pi is of full rank, okay, in that case R is equal to n. Since pi is also an n by n matrix, the rank of pi will be equal to n if it's of full rank. Then the long run solution to equation 19. Okay, let's look at equation 19 again. This is delta xt is equal to this. The long run solution to 19 is given by the n independent equations. Okay. So remember that your pi matrix is again an n by n matrix, and you have n variables. Okay, so because of that, your coefficients of the pi matrix will have this form. Okay, if I
Ma'am, could you repeat that where R is 0? Could you just
okay,
repeat that again, please?
yes, just a minute. Okay, so here, if the rank of the pi matrix is equal to 0, okay, then each element of the pi matrix has to be 0. That's what we've learned earlier also in the case of the square matrix A. The rank of the matrix will be equal to 0 only if each element of A is equal to 0. Okay, so in that case, 19 will be equal to an n variable var in first differences. So if all the elements of pi are equal to 0, so when you multiply pi with xt minus 1, this whole term will basically vanish. So you'll be left with only delta xt is equal to epsilon t. So that's why it says that it will be equal to an n variable var in first differences. Because if I rewrite this equation again, it will be equal to xt is equal to xt minus 1 plus epsilon t. Okay, it will have this form. So here they've written in terms of the elements of your xt vector. So that's why you have xit being denoted here. It will denote each of the n variables in the xt vector. So if you look at this equation now, each equation that you write for your var model will have this form. Okay? So all the xit sequences are basically unit root processes. The reason we are saying that is because the coefficient attached to this first lag is equal to 1. There's no coefficient given, right? It's we are not writing a1 or alpha 1 or anything. So we already know that the coefficient value is equal to 1. That's why we need not write it. So in that case, we can understand that this is a unit root process or a non-stationary time series that we are looking at. So each of the n variables in the xt vector are basically non-stationary variables or unit root processes which basically follow a random walk. Okay? And there is no linear combination of these variables that will be stationary. Now, if we want to find a linear combination of the variables that is stationary, then we need to find some parameter values where the linear combination of the two variables will actually become stationary. Okay? But it is not the case over here. Since this coefficient is equal to 1, you can understand that all your variables are basically following a random walk. They are unit root processes. So there's no combination of these variables that will actually be stationary. Now at the other extreme, if pi is of full rank and the rank of pi is equal to n, then in that case, the long run solution to equation 19 is given by the n independent equations. So here you'll have these n independent equations where since pi is of full rank, you'll understand that all the n rows or columns of the pi matrix are linearly independent. Okay, they are not evolving together or they are not following a common path in terms of their dynamics over time. Okay? So in that case, the long run solution to equation 19 is given by the n independent equations. Okay? So since it's a long run solution, it's taking this form. You're not seeing any lags over here. Okay? So you'll find that here, basically, if you write out this equation is telling you that all these variables are in equilibrium. Okay? But they do not have a common, to put it in very simple words, they do not share any sort of an equilibrium relationship because they are all independent variables. They are not evolving together or they are not related. So there's no question of any disequilibrium arising in their relationship and then them trying to adjust slowly towards equilibrium. Okay? So here, because all the n equations are independent or n rows are independent, the long run solution to equation 19 is given by each of these n independent equations again, where all these terms are equal to 0 when they are multiplied by the parameters of the pi matrix. Now each of these n equations is an independent restriction on the long run solution of the variables. The n variables in the system face n long run constraints. Okay. So here each of these variables, they will be evolving in a certain fashion. They will be constrained in some way by these n equations. Okay. Now in this case, each of the n variables contained in the vector xt must be stationary with long run values given by 20. Long run values given by equation 20. Okay, so in the long run, these variables will have this sort of a long run solution. Okay. And you will find that all these variables are actually stationary. Remember that for co-integration, we need the variables to be non-stationary. Okay. But here we find that each of the n equations are independent or n rows are independent. On top of that, the variables contained in the vector have to be stationary. Okay, if they are, if you find that the rank of the pi matrix is full, it will mean that all the variables are stationary. So there is no question of co-integration over here. Okay, so the variables cannot be co-integrated since all are stationary. Okay, so two conditions for let's say co-integration are not satisfied here. Okay, for co-integration, you need the variables to be integrated of the same order. Again, you need them to share some sort of an equilibrium relationship. So here, each of these variables seem to be evolving independently in some sense. Okay, they are, all the n rows are linearly independent. So there's no question of any sort of equilibrium relationship existing here amongst these variables. Okay, so that's why there's no possibility of co-integration if the rank of the pi matrix is equal to n, or if the pi matrix has a full rank. Now what we are interested in for the Johansson co-integration test is the intermediate cases where the rank of the pi matrix lies between 0 and n. Okay, so some positive value where r is less than n. Okay, so in that case you will find that there are r co-integrating vectors. So r could assume the value 1, 2, okay, any number but less than n, some positive value that is less than n. And r is also equal to the rank of the pi matrix. Now with r independent equations and n variables, remember we are going to arrange our pi matrix again so that the top portion of this matrix has all the linearly independent rows, okay, or linearly independent equations, since we are talking about some kind of a var model. So the r independent equations or linearly independent rows will come right at the top, and you will have the remaining n minus r rows at the bottom where there is linear dependence between the rows. Okay. So with r independent equations and n variables, there are r stochastic trends in the system. Okay, remember that in the previous class when we were discussing the Engel-Granger test and so on, we were discussing how co-integrated variables, they generally share a common stochastic trend. Okay, and the co-integrating vector will be such that it removes that common stochastic trend from the equilibrium relationship of those variables. Okay, it purges the variables of that common stochastic trend, and then you are able to find that they share some sort of an equilibrium relationship. Okay, so with r independent equations and n variables, there are r stochastic trends in the system. So there will be r common stochastic trends in the system, and what we need to do is find the elements of these the pi matrix so that we can get the co-integrating vector. Once we get this co-integrating vector, we'll be able to purge the system of these common stochastic trends so that the linear combination of these variables will now be stationary. Okay. So if R is equal to 1, okay, if the rank of this pi matrix is equal to 1, then there is only one co-integrating vector which is given by any row of the matrix pi. Okay? So we can use any row of the matrix pi for our work related to the Johansson test. Okay, we'll see exactly how in the next equation that we come across. So if the rank of the pi matrix is equal to 1, then there's only one co-integrating vector. Okay, if it's equal to 3, there are 3 co-integrating vectors and so on. Okay? But the number of co-integrating vectors has to be less than n over here. We don't want a full rank matrix. Then each xit delta xit sequence can be written in error correction form. Okay, remember that if the variables are co-integrated, then we can understand the short run behavior of these variables using the error correction representation, okay, which we discussed in the previous class again for the Engel-Granger co-integration test. Okay, so there we discussed how adjustment will take place in different time periods, and in each period gradually the speed of adjustment coefficient will tell us how much these variables are changing in response to disequilibrium so that the system returns to a state of equilibrium again. Okay, so for example here, since we're saying that each of these xit sequences, delta xit sequences, can be written in error correction form. Okay, for instance, let's take up the first equation of the VAR model here. Okay, so this model will have the first equation taking this form, delta x1t, denoting the first variable in the system. So your first equation again will have the form of given on the right hand side. Okay, so this will represent the first row of your pi matrix. Okay, pi 1 1, pi 1 2 to pi 1 n. Okay. So this is giving us the first row of this VAR model basically. So now what we can do is, so that we can get this equation in the error correction form, we need to manipulate it slightly. Okay, so what we do is we normalize with respect to x1t minus 1. Okay, we are discussing the case where r is equal to 1 over here. So we are normalizing with respect to x1t minus 1. You can pick any row, all right? There's no problem. You can pick any row. So what we do is we normalize with respect to x1t minus 1 by setting alpha 1 is equal to pi 1 1. So we select this, the coefficient which is attached to the variable which we have selected for normalization. So setting alpha 1 is equal to pi 1 1 and beta ij is equal to pi 1j by pi 1 1. Okay, we obtain this equation now. Okay, I'll let you look at equation 21 for a minute. Let me know if you have understood it or if I need to explain it. Would you like me to explain equation 21 or is it something that you'll understand?
Mom, equation 21 is fine for me. Could you please just scroll once up?
Okay.
I'm a little new on this. Okay, thank you, ma'am.
Just in case somebody hasn't understood, what we're doing here is in brackets, okay, you're writing a new set of coefficients attached to x1t minus 1, x2t minus 1, and so on. Okay, so these coefficients are the beta ij's over here. Okay, these coefficients. So here attached to x1t minus 1, since we selected this for normalization, we haven't written beta 1 1 over here. Okay, so beta 1 1 is basically equal to 1 over here. Okay, since beta 1 1 is nothing but pi 1 1 by pi 1 1. Okay, so that's why we haven't written beta 1 1 over here. You simply have x1t minus 1. Then beta 1, 2 is nothing but, again, pi 1j. Since we are looking at the second column of the matrix, it will be pi 1, 2 divided by pi 1, 1. Okay, this is beta 1, 2. Similarly here, I hope you have got the drift now. So beta 1n is nothing but here pi 1n. Okay, since you're looking at the nth column, it will be pi 1n by pi 1, 1. This is your beta 1n, this new coefficient. So here, what is alpha 1? Alpha 1 is simply pi 1, 1. Okay, and alpha 1 here will give you the error correction parameter or the speed of adjustment parameter. So if you remember the form that we were looking at in the Engel-Granger test of the error correction model, within brackets you have the, in some sense, the co-integrating vector and the linear combination of these n variables. Okay, so over here, what you're looking at is the equilibrium relationship between these variables and what is the deviation from that equilibrium. Okay, since all these variables, we believe that they share some sort of an equilibrium relationship, this alpha 1 will tell you how this particular variable is going to adjust to the disequilibrium in the relationship between all the variables in your var system. Okay, so this will give you the speed of adjustment of this particular variable. Okay, and these terms are basically telling you about the equilibrium relationship and what sort of adjustment is going to take place in the equilibrium relationship. Now, in the long run, the xit, okay, all these variables, okay, which are basically time series, they will satisfy the relationship x1t plus beta 1, 2, whatever is given in brackets. So there will be no disequilibrium in the long run. That's why this equation here or this term in brackets will basically be equal to 0. So there will be absolutely no disequilibrium in the long run, and all variables will assume their long run values where they are in a state of equilibrium with regard to each other. Okay, so there's no need or no tendency for any change to take place in any of these variables or one variable to adjust to the other. Okay. Now the normalized co-integrating vector is 1, beta 1, 2, beta 1, 3. Okay, all these parameters that you have here within the brackets. So this is called the normalized co-integrating vector, since we are normalizing with respect to x1t minus 1, so that we can write the equation in the error correction form. Okay, and alpha 1 is the speed of adjustment parameter. Now in the case where you have two co-integrating vectors, the long run values of the variables will satisfy the two relationships, okay, which are given by this. This will be the relationship that will be there between these variables in the long run. Okay, so that's why it's equal to 0. There's no disequilibrium at all. And again, you can appropriately normalize these variables. Okay, so you can pick one variable for normalization. You can also pick x2t, x2t, x3t, any of these variables, okay, for normalization, and then you'll set up your equations accordingly. So here, I think I incorrectly uploaded this page first. So we'll have to go to the next page and then come back to this page. Any doubts or questions so far? That portion will be slightly tricky. So I'll send the notes across to you today. Please go through it, all right? And let me know if you have any doubts. Any doubts or questions so far? Remember, if the rank of the pi matrix is 0, that means that all the elements of the pi matrix are 0 and all variables are basically non-stationary. So there's no linear combination of the variables that will be stationary. Okay, so in that case, there will be no co-integration. Also, the other extreme cases where pi is of full rank, there it means that all the variables are basically evolving independently of each other. Okay, all the linear equations are basically independent. So again, there's no question of co-integration over there. Okay, So we are interested in the intermediate cases where the rank of the pi matrix lies between 0 and n. So you could have the rank being 1 to any number which is less than n. And when you're setting up the var model and the error correction representation of the var model, okay, or the VECM as we addressed it in the previous class, in that case, you'll be normalizing with respect to one of the variables so that you can create the speed of adjustment parameter. And then you'll be looking at how these variables adjust to each other, okay, in cases of disequilibrium in the short run. Yes, somebody was trying to say something. Any doubts or questions?
No, ma'am, I don't think so.
Okay.
Also, ma'am, which two pages have been rearranged?
I'll put it in the correct order for you, all right? So this was page 12. So after page 12, I accidentally uploaded page 14, okay, instead of 13.
Okay, ma'am.
I'll
Noted.
do it correctly and send it to you, so you don't have to worry about that. So here, now we are discussing Johansson's method. Now that we've understood how exactly we'll be setting up the equations and so on. So let's see what Johansson's test for co-integration actually involves. Okay, so would you all like a break for a few minutes? I think I'll be continuing only for another half an hour. Would you like me to stop for 5 minutes?
Yes, ma'am, that would be nice.
Okay, fine. Yeah. So we'll meet in 5 minutes. It's 3:33. We'll meet at 3:38. Right? Okay, I hope all of you are back. I'll begin the class again. Okay, so now we are discussing Johansson's method of testing for co-integration. So he devised this method in 1988, and again it uses all these concepts that we've been discussing so far, the rank of the matrix pi, to test for co-integration. Okay, and it also helps us generally to find the co-integrating vector also. Now, in general, if the rank of pi is unity, okay, so if the rank of the pi matrix is equal to 1, then all rows of pi can be written as a scalar multiple of the first. Okay, so this is what we saw in the numerical example also that we discussed. So all the rows of that A matrix could basically be written as a scalar multiple of the first row itself. Okay, so here each of the delta xit sequences can be written this way. Okay, so this is basically your scalar over here. Okay, and within the brackets again you have that equilibrium relationship. You'll be able to find the co-integrating vector using this. Okay, and you have epsilon it. So S1 is equal to 1 and Si will be equal to pi ij by pi 1j. Okay, so again similar to what we discussed over here, the same sort of approach is being taken. Okay, similar to what we discussed on this page. Okay, so a similar sort of approach is being taken over here in the Johansson co-integration test. So here again you're normalizing with respect to one of the variables. Okay, so suppose you pick x1 t minus 1, so then s1 will be equal to 1 in that case, and you'll find alpha 1, or this is basically your alpha 1 over here, si. Okay, so that will be equal to pi 1 1 if you're selecting this for normalization, and si will be equal to pi ij by pi 1j. Now the linear combination which is given in the brackets will then in that case be equal to delta xit minus epsilon it by si. Okay, and this will be stationary since delta xit and epsilon it are both stationary. Okay, remember, since we are dealing with non-stationary variables, if you take the first difference of all the xit variables, they will be stationary. Okay, so this variable itself will be stationary, and this is also stationary, and since this is some scalar, so in that case you'll find that this whole term will be stationary, and this linear combination that is there in the brackets will be stationary. So these elements pi, or these parameters, will basically give you the co-integrating vector over here. Now the rank of pi equals the number of co-integrating vectors. Okay, if the rank, just a moment. Yeah, sorry about the interruption. So if the rank of pi equals the number of co-integrating, if the rank of pi is equal to r, that means that there are r linearly independent combinations of the xit sequences that are stationary. Okay, so this is again similar to what we've learned earlier. Okay, so if rank of pi equals 0, obviously all the elements of the pi matrix are equal to 0, and there's absolutely no co-integrating vector there. Okay, then if the rank of pi is equal to r, okay, there are r linearly independent combinations of the xit sequences that are stationary. Since there are r linearly independent rows, okay, so there will be r linearly independent combinations of the xit sequences that are stationary, and if the rank of pi is equal to n, okay, or if it's a full rank, that means that all the rows are linearly independent, so there's no question of any sort of equilibrium relationship between the variables, and there's no co-integration because all the variables are now stationary. Okay, Now the rank of pi is equal to the number of its characteristic roots that differ from 0. Okay. Remember, the rank of any matrix is equal to the number of its non-zero characteristic roots. The same thing is being stated over here in the context of the pi matrix. So what we need to do is first arrange the roots in such a way. Once you have solved the characteristic equations and you are able to get the characteristic roots, you'll basically arrange them in this fashion, okay, in ascending order. So lambda 1 greater than lambda 2 and lambda n should be the smallest. I mean, whichever is the smallest value, you'll put it at the end, okay, at the very end. The largest value will come first and then the smallest value at the very end. So the Johansson methodology allows you to determine the number of characteristic roots that are significantly or statistically different from 0. Okay. So that will help us to find the rank of the pi matrix, and it will tell us how many co-integrating vectors there are. Okay. So the method that is used in the Johansson test, please stop me if you have any questions at any point. So the method that is used is as follows. Okay, so here if you have a var model, which is a pth order var model, so there are p lags of all these n variables over here. So it's a pth order var model. Now to go back to the previous page, right? That's why I'm moving up. First, what we need to do is find the appropriate lag length for the var model. Okay, how can this be done? How can you select the lag length for the var model?
The first thing that I would prefer doing is trial and error.
Okay.
And then
But if you have some sort of criteria or anything, what criteria would you use to select the lag length?
for the VAR,
Yes.
I think correlation and auto correlation for itself.
Okay, you're thinking of this ARIMA models, I think.
ARIMA model, yes.
Okay. I had briefly mentioned for VAR models, you can use a kike information criterion. Is that what you were going to say? Somebody was answering.
I think as we discussed in VAR, I think it should be until the point that the impact over the period is because of itself instead of the other variables. I might be wrong in phrasing the words.
Okay. See, generally, to select the lag length for any VAR model, you can use the archaic information criterion or SBC. Okay, any of these. There are few others also, HQIC or something like that. Yeah, Hanan Quinn information criterion. So you'll get different ones with different software, but the two most popular ones are AIC and SBC. So the same criteria that you were using for model selection for ARIMA models, there are versions of those, multivariate versions of those for selecting the lag length for VAR models. All right, so those are readily available in the software. I've included it in your notes also, how exactly it's calculated. So those criteria are used to select the lag length for a VAR model. You also have likelihood ratio test, but the simplest method that is generally used is using AIC or SBC. Okay, so you need not plot the ACF, PACF or anything like that here. That is only for ARIMA models. Okay. So what you need to do is first estimate the VAR model in first difference form. Once you've selected the lag length, okay, once you've determined what is P, then estimate the VAR model in first difference form as follows. So all the variables that are appearing on both the left hand side as well as the right hand side have to be in the first difference form. Okay. Then in the second step, okay, after this first step, what you'll be doing is using these errors here, E1T. Okay. Then in the second step, what you need to do is regress xt minus 1 on the lag changes now. So instead of taking delta xt, you'll take xt minus 1. Okay, the first lag of all the variables that are there in your var model. So you'll be regressing them on the lag changes now. Okay? The p lags of the changes in these variables, n variables. So you'll be regressing xt minus 1 on the lag changes. Then again from the second step, you're interested in the residuals from this regression. Okay? So in the third step, what we need to do is compute the squares of the canonical correlations between E1t and E2t. Okay, so once you have extracted the residuals from the first step and the second step, then what you will be doing, what is meant by this canonical correlations is basically you create the cross covariance matrix. What is the covariance between E1t and E2t, these two sets of residuals? Okay, you first find that out, and then canonical correlations is basically a method which will help you find linear combinations of these residuals in this case that have the maximum correlation. Okay, that's what canonical correlations means. Whenever you're calculating canonical correlations for any two sets of variables, basically you're finding linear combinations of these variables that have the maximum correlation. Okay, after creating their cross covariance matrix. So you actually don't have to do all this. The software does it for you, but just to help you understand what is the method that Johansson employed, we are discussing it. Okay. Now, in an n equation var, you'll find that there are n canonical correlations and there are n values of lambda I. So there are n characteristic roots. Okay, since your pi matrix for this n variable var model, you will have again a pi matrix. Remember, this is only for the Johansson test, all these steps that we are discussing. So in this var model, basically, since you will be using n by n square matrices all the time, okay, so you will have n characteristic roots. Okay, so the n canonical correlations again are the n values of lambda I. Okay? And these lambda I are obtained as solutions to this equation. Okay? Again, you don't have to bother too much what these equations are. Okay, you're trying to find out what is lambda I, solve for lambda I itself. Okay, so here what is S22, S12 and so on. Okay, so if you look at this, okay, SII, so this refers to both S11 as well as S22. Okay, so what is SII? SII is nothing but your variance, what do you say, a vector of your variance values. Okay, for these error terms, you'll be basically calculating the variance over here using SII. So S11 and S22 basically give you the variance of the residuals. Then what does S12 give you? Obviously, it will give you the covariance here. Okay, so this gives you the matrix, covariance matrix, and this gives you the variance. So where E1t and E2t are the column vectors of residuals from steps 1 and 2. Okay. I hope so far it's clear to all of you. So basically you will be creating this equation. Once you've extracted the residuals E1t and E2t, you'll be able to find out their variance and the covariance. Okay. Then after that, you will be able to create this equation and solve for this equation. Okay, the determinant of this matrix now has to be equal to 0. So you'll be able to solve this equation and find out what is lambda I. Then for the Johansson test, my maximum likelihood estimation is used. So the maximum likelihood estimates of the co-integrating vectors are the n columns that are non-trivial solutions for this. Okay. So this portion might seem slightly complicated. It's generally not discussed. I'm just doing it for your information. All right. So here, once you get, once you are able to solve for lambda I, then you can create this also, pi I, okay, this matrix that you have from your original var model. So then in that case, the maximum likelihood estimates of the co-integrating vectors are the n columns that are non-trivial solutions for this. Okay, so here you'll be able to get n columns from this step. Okay, it may not be very clear to you. It's not very clear to me also, since I haven't manually done it. Okay, but remember that we are trying to find the co-integrating vectors which will be contained in the parameters of this pi matrix. Okay. So thus we can determine the number of co-integrating vectors. We can find out exactly how many co-integrating vectors there are, because the number of non-zero lambda i's will give you the rank of pi, which will again tell you how many co-integrating vectors there are. If you can directly find the rank of the pi matrix, also you'll be able to find out how many co-integrating vectors there are. Okay. Now to test for co-integration itself using the Johansson method, okay, we use the following two test statistics. One is known as Lambda Trace and the other is Lambda Max. Okay. So Lambda Trace does not have a very specific null hypothesis, but Lambda Max has a specific null and alternative hypothesis. Okay. The next page, I think, lists what exactly these are. So remember that this is how this test statistic is calculated. Again, this is the rank of your pi matrix R, okay, which will tell you how many co-integrating vectors there are, okay, for your particular var model. Now, since we are calculating this statistic and it has this form ln1 minus lambda I hat, okay, remember that if any of the lambdas are, or if all the lambdas are, lambda values are equal to 0, okay, that means that there are absolutely no non-zero characteristic roots and the rank of your pi matrix will be equal to 0 in that case. Okay, so here we need the rank to be some positive value, right? So there must be at least one non-zero characteristic root. So when you're calculating the statistic, if this is equal to 0, if any of the lambda i's are equal to 0, then ln1 is also equal to 0, right? So in that case, lambda trace will be equal to 0. Okay? So in general, if you have at least one co-integrating vector, or if the rank of the matrix is at least equal to 1, which means that there is at least one non-zero characteristic root, then lambda I will lie somewhere between 0 and 1. Okay. So if it lies somewhere between 0 and 1, then you will find that this term has to be some small value or negative value. Okay. So here, this is how lambda trace is calculated. Then for lambda max, you'll be calculating r plus 1. So generally, the null hypothesis and alternative is listed on the next page. So I'll take you through that. Okay, where the lambda are the estimated values of the characteristic roots, also known as the eigenvalues, which are obtained from the estimated pi matrix. Okay, so basically you'll be estimating the pi matrix. From that, you'll be able to get the estimates of the characteristic roots and so on. Okay, and t is the number of usable observations. So once you've taken lags, differences, and so on, how many observations you're actually left with for estimation, that will be equal to t. Okay, so lambda trace here tests the null hypothesis that the number of distinct co-integrating vectors is less than or equal to r against a general alternative. Okay, so here the null is not very specific. So it's telling you that the number of co-integrating vectors could be less than 1 or equal to 1. So it could even be 0 over here. Okay. And the alternative hypothesis is also very general here. So the number of co-integrating vectors according to the alternative hypothesis, it's something greater than 1. So it could be 2, 3, 4 up to n. Okay. or of course it will be less than n, but any number which is greater than whatever is stated in the null but less than n. Okay, so it's a very general sort of null hypothesis. Now lambda max is more specific. Okay? So lambda max tests the null hypothesis that the number of co-integrating vectors is r against the alternative of r plus 1 co-integrating vectors. Okay? So here it will be very, very specific, and if you look at how the statistic is calculated also, it's given over here. Here you'll be using lambda hat r plus 1. Okay, so whatever estimate you get for r plus 1 co-integrating vectors, that is the one you'll be using over here to calculate your lambda max statistic. Once we do the practicals, you'll understand better exactly how this is used. Yeah. So here lambda max tests the null hypothesis that the number of co-integrating vectors is r against the alternative of r plus 1 co-integrating vectors. So if the estimated value of lambda r plus 1 is close to 0, then lambda max will be small, okay, in that case. So this also you can see very clearly from the way the statistic itself is calculated. Okay, so here once you've calculated these lambda trace and lambda max statistics, you'll be comparing with the distribution. Okay, so there's a particular distribution which was developed by Johansson and others subsequently. So you'll be comparing with those critical values. Okay, so again, as usual, you'll find that if the calculated value of the test statistic is greater than the critical value, then you will be able to reject the null and accept the alternative hypothesis. Now for lambda trace, if all the lambda are 0, then lambda trace is equal to 0. Okay? Then the further the estimated characteristic roots are from 0, the more negative is ln 1 minus lambda I hat. Okay? So this term itself will be, since lambda is supposed to lie between 0 and 1, this is what I was telling you all earlier. Since it's supposed to be lying between 0 and 1 if the characteristic roots are non-zero, in that case this value will be some small number, and because of this minus sign it will be negative. Okay. So here the more negative is ln 1 minus lambda I hat, and the larger will be the lambda trace statistic. Okay. In both cases, if the calculated test statistic is greater than the tabulated critical value, reject H naught. Okay. So again, when you're looking for the critical values for the Johansson test, it will be in a particular form. So the table, again, it has different sets of critical values if you're including a drift term, or if you're including any sort of deterministic regressors in your regression, then the critical values are slightly different. If you're including a constant in your regression, it's different. If you're including a trend in your regression, it will be slightly different. And again, just like how you have degrees of freedom, here you'll be looking for or checking against n minus r, okay, where n minus r is the number of non-stationary components in your var model. Okay, so how many non-stationary elements there are in your var model, or variables there are in your var model, you'll be comparing against that when you're checking for your critical values. So this part, understanding the how exactly you draw conclusions from the Johansson test, might become a little easier once we actually do the practicals. So I'll try and take you through that maybe in the next, not in the next class, the next to next class. Okay, we'll do practicals. So until then, what you basically need to understand about this test is it helps us to find the elements of the pi matrix, which will give us the co-integrating vectors. Okay, then also based on the number of non-zero characteristic roots, you can draw conclusions about what is the rank of this pi matrix and how many co-integrating vectors there are. Okay. Once you have found the co-integrating vectors, obviously you will find the co-integrating relationship or equilibrium relationship, and then again you will be able to estimate an error correction model, so you can understand what is the short run behavior of these variables and the long run behavior of these variables. In the long run, this whole set of terms will be equal to 0 since the variables are in equilibrium, okay, or the system is in equilibrium actually. Any doubts or questions? I don't expect you to understand this portion completely, okay? But any doubts or questions related to this?
Not as of now, ma'am.
Okay, fine. So once I share the notes and once we do the practicals, try and go through it again. So that will help you understand a little better. Okay. So I'll be sharing these notes with you all today. I will stop here at this point because the next topic that we'll be dealing with is volatility models. I don't want to start it today. There should be some continuity in the class. So I'll take it up in the next class. All right. I wanted to know when do your tests end?
Ma'am, on Monday.
They
No,
start
it
on
starts
Monday.
on Monday and it
Yeah.
ends on
Friday, is it?
Friday. Yeah.
And you're supposed to have classes right after that, no?
Yes, ma'am.
So is it okay if I take the class on Friday?
Ma'am, I think that's a trick
That's why I
question.
asked you.
Ma'am, actually, Friday is going to be 31st, so I think it'll be nice if we
You
don't.
want a break, huh?
Yes, ma'am.
Okay. All right. Then would you all mind if I take classes in January? Your
Yes, that
your end semester exams are there on I think FE is on 17th, if I'm not
yes, ma'am. It
mistaken.
starts with FE on 17th.
Yeah. So yeah, 31st is a Friday. Okay. So I don't think y'all will be in the mood for a class. So Saturday also I don't, would you all like, or would it be okay for me to take a class on Saturday? Saturday is 1st Jan.
Ma'am, we can have classes in January, but let's skip 31st and 1st.
Okay, yeah, fine. So let's actually have a happy new year. So no class then on 31st and 1st. So
Thank
after
you.
that, can you all let me know when you all will be free for a class? If you all somebody can coordinate and just let me know.
Yes, ma'am. I can do that with you. I'll email you.
Okay, fine. So Cherry, please check with both batches, all right? IBF and FE both, and let me know when you all will be free for classes in Jan. I think we need to take approximately 4.5 session hours are left, I think. So uh, I'll definitely wrap it up in that time. And one of the sessions will be taken by Professor Kamaya, I think at least a 1 hour session. So if you can let me know for 4.5 hours when you all will be available, okay, by mail, if you can do that, I'll be really grateful to you, Cherry.
Ma'am,
Yes,
it's fine if it's over 2 days, right?
Yeah, it can be over 4 days also. I don't mind.
Yes, ma'am. Yes,
Okay,
ma'am. I
but
think Cherry
as
can coordinate with you. I
yeah, okay. So please find out from both the classes and just let me know. And we'll I might not be able to do the practicals fully, but I will definitely send you the R script with comments so that you can do it on your own. Okay, so maybe in one of the classes, once you'll have tried it, then we can see if you are having any problems somewhere and we can discuss it.
also, ma'am, just confirming we don't have a class tomorrow, right?
No.
Okay.
Okay. Let's celebrate all the festivals and have a happy new year, and we'll meet after that. All right. So, yeah. So that's it from me for today. I'll send you all the notes. Please go through them and please prepare well for your test. And I've kept it quite simple. Don't write anything extra, okay? I don't give marks seeing the length of your answer. So please be precise. Even if it's a short answer, if you have included the most important points, then it's enough. All right. Thank you for your time. I'll see you in January. Please get in touch with me, okay, Chairi?
Yes, ma'am. Definitely.
Yeah.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you, ma'am.
Bye.
Thank you, ma'am.